Now we come to one of the great triumphs, the second triumph of the Big Bang Theory, the idea of primordial nucleosynthesis. We know that when the universe was born, it was probably only had things that were the fundamental particles like protons, neutrons, electrons. And yet today we see a universe full of many other things, full of hydrogen and helium and then lesser amounts of heavier elements. Can we go through and can we predict how much stuff there is in the universe?
So what must have happened is nuclear fusion. We must have combined these subatomic particles, say the protons and neutrons, to make heavier elements like the carbon in our own bodies. This is called nuclear fusion because we're sticking things together. The trouble is that nuclear fusion is a very difficult reaction to make work. Normally, you take two nuclei together and they're both positively charged because they contain protons, and like charges repel, so these things will squirm around and avoid each other, as you can see in the simulation. Here I've got a whole bunch of positively charged protons and you can watch them all avoid each other. Whenever they get close they suddenly veer away.
Kind of reminds me of a few parties I've been to, Paul.
Indeed, yes. So nuclear fusion is hard. To make it happen you need two things. You need very fast moving particles, very energetic particles, and you need a very high density to make sure these collisions happen a lot.
So we know from our earlier work that when we go back in time, the scale factor becomes smaller, which leads to the average density of the universe increasing and the average energy per particle increasing. So as we go back in time, we can make a universe which is hotter and denser. And at some point, we can even exceed both the density and temperature of the center of the sun, a place that we know nuclear fusion occurs. So it would seem that we should be able to create a lot of fusion in the universe's past.
Indeed, in fact the problem is too much fusion probably. By the time we're down to a universe that's 10 to the 10, it's 10 billion times smaller than today, it's both it's as dense as the center of the sun and far hotter, so it should be a perfect place to produce an immense amount of fusion. The trouble is, if you have lots and lots of fusion going on, eventually you're going to form iron. Iron is the most stable element, so you'll fuse everything else to iron.
So that's just like the center of a supernovae, where it's both hotter and denser than the sun.
And that produces a ball of iron. So that's what we should be getting here. We should have an entire universe that only contains iron, nothing else. Everything else should have been fused to this, the most stable element. And that would be a pretty bleak universe to live in, because iron can't get any more fusion power out. So you can't have stars in a universe that's made of iron. It would have to be a cold, dark universe with no radiation, just iron balls or black holes drifting around. No place for life.
So let's look at a few important numbers that surround how nuclear fusion takes place in the universe.
Now, it turns out that nuclear fusion is possibly the best researched part of astrophysics. The reason is that this science is very useful for killing huge numbers of people, known as hydrogen bombs, and therefore governments put huge amounts of money into researching it. And luckily we astronomers can borrow their results and use them to understand the early universe. So some key numbers. When the universe was 10 seconds old, density was about 1 ton per cubic centimetre.
It's pretty dense. And another key number is that the neutron, you may not realize this, is not stable unless it's bound in a nucleus. It has a half-life of 887 seconds. So if you just let it, it's going to go through and break apart and no longer be a neutron.
Which is a problem, because it means we have to get all the neutrons bound up in something before 887 seconds. That's about 15 minutes. If they're not bound by then, the neutrons will go away, and we end up with a universe with no neutrons, which is a universe entirely of hydrogen. I guess there'd be stars in this universe. It's better than the iron universe, but you kind of need elements other than hydrogen, all of which involve neutrons, to have life. So it'd be a universe full of stars, but no one to marvel at how beautiful they are.
And finally, we also have to worry about something quite subtle, the binding energy of deuterium.
Why does deuterium matter here? Well, it turns out there's what we call the deuterium bottleneck. Whenever you're fusing stuff, the first step is normally to combine a proton with a neutron to form deuterium, which is just a proton plus a neutron bound together. Why is this the first step? It's the first step in most nuclear reactions because it's very easy, because, well, this is positively charged, that is not. So there's no repulsion between these two, so they can actually stick together very easily. And so nearly all reactions start off by forming deuterium, and then you combine deuterium with something else to make heavier elements.
But one of the problems with deuterium is it's very easy to form, but it's also very easy to destroy. And so if we go back to when the universe was very hot and dense, it's full of photons, very energetic photons. Photons so energetic that they can go through, and as soon as a deuterium atom is created, it can be destroyed instantly by one of the multitudes of high-energy photons traveling through the universe at that time.
These being the same photons that we see in the microwave background now, only obviously much more energetic back then.
And you really have a race on our hands here, because as you create deuterium, which we're going to build everything else out of, it gets destroyed. And so you make deuterium, it gets destroyed, and it is really a race to go through and create elements before 887 seconds has elapsed, and we lose all our neutrons.
So, proton forms with neutron, forms deuterium, blown apart. Deuterium, blown apart. Deuterium, blown apart. The clock is ticking. 10 seconds have gone. 20 seconds, 30 seconds, a minute. Still, we're getting the first step of fusion, but nothing else. A sea of photons is just ripping everything to pieces. But then, by great relief and great fluke, because of course the clock has been ticking the whole time, those neutrons have been disappearing. After 90 seconds, it just so happens, you do the numbers, that the energy of the photons drops below the binding energy of deuterium. And at last, deuterium can actually form and stay formed.
So we can put together a proton and neutron, make deuterium, and it stays. And that allows deuterium to, for example, combine with, for example, other elements to produce other things such as helium-3 or tritium, that's hydrogen with 2 neutrons. And eventually all these roads lead to one place, which is helium. Helium-4, one of the big things that is in the universe. And this whole nuclear reaction, turns out, network, which we know very well thanks to our nuclear energy weapons programs, really predicts that 25% of the universe should be in the form of helium.
While this has all been going on, the universe has been cooling down, getting less dense, the energy of the particles has been dropping, and it turns out that by the time we're producing large amounts of helium-4, so a minute and a half after the Big Bang, the energy has dropped so far that this is where the reaction stops. You don't then go on and combine, say, 3 helium-4 nuclei together to form carbon, and all the way on to iron. It's too late. The density is now so low, the energies are so low, that after about 3 minutes, the nuclear reactions stop, and you're just left, as Brian said, with 75% hydrogen, 25% helium, plus trace amounts of other things like deuterium.
So we can go out and we can check this universe and say, does it have that amount of helium? Does it have that amount of deuterium? And see how it squares up.
This was first done by J. Norman Lockyer in 1868, who pointed a spectrograph at the sun and discovered helium. And it seems to work. The universe today is indeed made up 75% of hydrogen, 25% of helium. I mean, there are some small amounts of other crap like your carbon and nitrogen, like in our own bodies, but in the overall scheme of the mass of the universe, they're almost irrelevant. The universe today is still what it was left as 3 minutes after the Big Bang, by and large, 75% hydrogen, 25% helium.
And that other stuff, the carbon, we have reasons to believe, which we'll talk about later in the course, that that stuff was not formed in the Big Bang at all, but it's been formed by subsequent generations of stars.
So this is the second great triumph of the Big Bang theory. That you put in the numbers and you find out you don't fall into the trap of having a universe entirely of iron, or a universe that's only protons and no neutrons. We're just in the middle, because of the coincidence between energies of photons, binding energy of deuterium, and the half-life of neutrons all happen to average out to give us the universe we live in.
So if you want to have a good theory of the universe, you're going to have to explain why there's the abundance of the elements that we see, at least with respect to helium and deuterium.
Good.